In this video, I'm going to tell you how to evaluate integrals which involve products of powers of trigonometric functions. To begin with, let's look at an integral which is a product of powers of sine and cosine. First, if the power of sine is odd and positive, then what we're going to do is convert all but one of the sine factors to cosines using this Pythagorean identity. Sine squared equals 1 minus cosine squared. This is just a trigonometric identity which hopefully you've learned at some point in your math career. Once we make this transition to cosines, we then let u equal cosine and go from there. As an example, let's take a look at this integral. It's sine cubed times cosine to the fourth. Now what we're doing is we're saving one of those sine factors over here. We're going to use this as our du later, but then we're going to change this sine squared to cosine squared by making use of the identity sine squared equals 1 minus cosine squared. And now we're going to let u equal cosine x, compute du, that's negative sine x dx, so sine x dx, this bit here, is equal to negative du. Now let's plug that in. This 1 minus cosine squared x becomes 1 minus u squared, cosine to the fourth x becomes u to the fourth, and as we said, sine x dx is negative, there's the negative, du. Okay, now this is just the integral of a polynomial, which is rather easy. We just distribute u to the fourth first, and then we can use the power on, the power rule on both of these terms. And then don't forget to back substitute, and here is our antiderivative. Similarly, if the power of cosine is odd and positive, then we're going to convert all but one of the cosine factors to sines using the identity cosine squared equals 1 minus sine squared. This is essentially the same identity, just rearranged. And then we let u equal sine x. I'm not going to give an example of that just yet. We'll see an example of this later. Okay, if the powers of sine and cosine are both even and non-negative, then what we're going to do is make repeated use of these trigonometric identities to convert to this second situation. Let's see how this goes. Suppose we want to compute the antiderivative of cosine to the fourth dx. Well, that's cosine squared squared, and cosine squared is 1 plus cosine 2x all over 2. That's just a trigonometric identity that was on the previous slide. So this is cosine squared squared. Okay, let's multiply that out then, since this is a fraction with two terms squared. So we FOIL that out, and we get 1/4 plus 1/2 cosine 2x plus 1/4 cosine squared 2x. Okay, well, let's do this again for this cosine squared here. Cosine squared is 1 plus cosine double the angle, that makes this 2x change to a 4x, all over 2. Alright, let's now collect like terms. With the constant term we have 1/4 plus 1/4 times 1/2. So that would be 1/4 plus 1/8, which is 3/8. 1/2 cosine 2x is here, and then we also have this term cosine 4x divided by 2 times 4, which is 8. So that's how I'm getting this line. And now we're ready to just make a simple u substitution for this integral and for this integral. So let's let u equal 2x, so du is 2 dx, and let's let v equal 4x, so dv is 4 dx. Then we can rewrite our integral as follows. We're going to make this substitution here. 2x is u, the dx was du over 2, that's why this became a 4 here, and then 4x was v, and dx was dv over 4, which is why this became a 32. Alright, now we have three basic integrals which we can just write down, and then don't forget to back substitute. Okay, let's consider what to do if we have an integral involving powers of secant and tangent. If the power of secant is even and positive, then we can convert all but one of the secant squared factors to tangents using this trigonometric identity. Secant squared x equals 1 plus tangent squared x. And then we let u equal tangent x. Let's see how this works. For this integral, we're going to save a secant squared factor for a du later. We plan to make a u substitution, u equals tangent x, and so the secant squared will be needed for the du. Next we're going to convert our secant squared factor into 1 plus tangent squared. The angle is still the same. If the angle was 3x before, it should still be 3x here. Okay, next we're going to make the substitution. We're going to let u equal tangent 3x, simply because 3x is the common angle among all these functions, so I may as well build that into my u. So then du is 3 secant squared 3x dx. And so let's rewrite our integral now. This 1 plus tangent squared 3x is now 1 plus u squared. Tangent cubed 3x is u cubed now. And then secant squared 3x dx is equal to 1/3 du. So we have a 1/3 du. Alright, and now we have the integral of a polynomial, which is easy. Distribute your u cubed first, and then use the power rule on each term. Then don't forget to back substitute. Next, if the power of tangent is odd and positive, then we're going to convert all but one tangent factor to secants using this same identity, just rearranged. Then we let u equal secant x. Here's a good example. The tangent is raised to power 3, so we're going to save one of those tangent factors for a du later. And then we're going to convert the other powers of tangent to secants using that identity. Tangent squared equals secant squared minus 1. Okay, now we let u equal secant x so that du equals secant tangent x dx. Then tangent x dx equals cosine x du, just by multiplying both sides of this by cosine. Then I notice that since cosine is just 1 over secant, that's 1 over u du. Okay, well then now we can rewrite our integral. Here's secant to the negative 1/2 x, that's just u to the negative 1/2. Secant squared minus 1 is u squared minus 1, and then we already noted that tangent x dx is 1 over u du. So let's multiply that out. So if I multiply this, distribute this to both terms, and then divide both terms by u, I get this, u to the 1/2 minus u to the negative 3/2, and now we can apply the power rule to both of these. And don't forget to back substitute, and here's our integral. Now if there are no secant factors, and the power of tangent is even and positive, then convert a tangent squared factor to a secant squared factor, then expand and repeat if necessary. So for example, if we want to compute the antiderivative of tangent to the 4th, what we do is break that up to tangent squared times tangent squared, and we're going to change that second tangent squared to secant squared minus 1 using that same trigonometric identity as before. Then we're going to distribute tangent squared to both terms. And now this first integral is already set up for using a u substitution, right? I mean, if I let u equal tangent x, then du will be secant squared x dx, and so I can use substitution there. But for this integral, I'm going to need to repeat what I just did. I'm going to need to change tangent squared x dx into secants. And so let's do that, using that same trigonometric identity as before. Okay, now let's do what I described earlier for this first integral. We're letting u equal tangent x, du is equal to secant squared dx, and so we can now rewrite our integral using that substitution. And then compute each of these integrals. These are all basic integrals, and then we back substitute. If the power of tangent is 0 and the power of secant is odd and positive, then we use integration by parts as we did in the example of integration by parts where we computed the integral of secant cubed dx. So, I mean, you could use that example before, or we can look at this example. Secant to the 5th x dx we can write as secant cubed x times secant squared x. Then we do integration by parts. Let's let dv be this secant squared x, which we know how to integrate. Then that becomes tangent x. The derivative of secant cubed x is 3 secant squared x because of the power rule. Then by the chain rule, multiply by the derivative of secant x, which is secant x tangent x. Okay, let's clean that up a little bit, combine the secants together. And let's write down what the integration by parts rule tells us. It'll be uv, that's secant cubed times tangent, minus the integral of v, there's a tangent, du. So v du is 3 secant cubed tangent squared. And so that's why we have this. Okay, next we're going to convert that tangent squared to secants using that same trigonometric identity as before. Tangent squared equals secant squared minus 1. Then we're going to distribute secant cubed to both of these terms in the parentheses and split up into two separate integrals. And then what we see is this same integral, secant to the fifth, appearing on the left and the right. We're going to solve for this algebraically by first adding 3 times the integral of secant to the fifth to both sides. So I get 4 times that integral equals secant cubed tangent x plus this integral, which we computed in a previous video. This is 1/2 secant x tangent x plus 1/2 natural log secant x plus tangent x. Okay, then divide by 4 and you're done. Now, if none of the above rules apply, then you might try converting to sines and cosines. So this is a good example of that. This doesn't fit any of the conditions of the first 4 rules for secant tangent. So let's just rewrite them in terms of sine and cosine. Secant is 1 over cosine, and tangent squared is sine squared over cosine squared, but since this is in the denominator, we've flipped that fraction here. So this is cosine squared over sine squared. Okay, let's multiply out, collect powers of sine and cosine. So of sine there's a power of 2, but in the denominator, so we have sine x to the negative 2. And let's see, we have cosine squared up here, and then cosine in the bottom, so one of those cosines cancels, and so we just have a power of cosine to the 1. Okay, now let's let u equal sine. Du is equal to cosine x dx, which is right here, so this integral can be rewritten as u to the negative 2 du, which we can evaluate using the power rule. And don't forget to back substitute, and we can simplify this easily, so let's do. Okay, if you encounter an integral involving sine-cosine products, but with different angles, then you can make use of the following trigonometric identities to change it into 2 integrals, which each are easier. Here's a good example of that. Sine of 5x times cosine of 4x can be rewritten using that using which of these? This identity right here. We can rewrite it in this way. Okay, and each of those is easy. The first one is a direct basic integral, but for this one we need to make this substitution. U equals 9x, du equals 9 dx, and so dx is d over 9. And so that second integral is rewritten this way. And now let's compute each of these. This first one is negative 1/2 cosine dx, this one is negative 1/18 cosine u, and then we have our plus c, but then we need to back substitute, replace that u with 9x. So to recap, basically there's just a set list of guidelines for evaluating trigonometric integrals. In the next video we're going to actually use these because we're going to learn a technique for integrating which will produce trigonometric integrals for us to solve, and that's called trigonometric substitution. But for now, please try your hand at these integrals, and I will see you in the next video.